Good morning, children. Yesterday, we talked about electric potential due to a point charge, and I told you that we define electric potential at a point or we define it as potential difference. I'll again repeat and we'll make you understand the definition. Suppose this is the charge and say this is the field around it. Then the electric potential, say at this point, due to this charge, say this is point A, will be the work done in bringing a test charge from infinity to this point. Now, here infinity means the test charge is already outside the effect of the electric field. And potential differences, suppose there is other point, say B over here. Then electric potential difference is the work done in moving the charge from point A to point B. And in this manner, we yesterday calculated the potential difference between 2 points A and B. The value came out to be 1 by 4 pi epsilon naught Q 1 upon RB minus 1 upon RA. This was the expression for potential difference. The same expression can be used to find out potential at a point. The only thing what we have to do is RA has to be taken as infinity. Now what we'll do here? RA will be taken as infinity and RB now you can take as equal to R only. Because when RA is taken as infinity, then whether I use B or C or D, that is immaterial. The distance will be only one distance, and that we can take as R. And now we can substitute the potential at a given point will be equal to 1 by 4 pi epsilon naught Q 1 upon R. So V is equals to 1 upon 4 pi epsilon naught Q upon R. So this is an expression for potential at a point, and this is an expression for potential difference. Now potential is a scalar quantity. And therefore, the negative sign or the positive sign of the charge is to be included in the expression itself whenever you are calculating it mathematically. Like in electric field and force, what we were doing? As far as the magnitude was concerned, we were not using the sign of the charge. The sign of the charge was used only for determining the direction. Here in this case, it will be used up in the expression itself, as it does not have to do anything with the direction. Now, as we had done in electric field also, that we found out electric field due to a point charge, and then we calculated, we defined electric dipole, and then electric field due to a dipole. Now, here also now, we will try to calculate potential at any point due to an electric dipole. Here we'll do only one derivation, that is at any point, and then can be limited to at an equatorial point or at an axial point or any value. Alright, so now we'll try to find out potential at any point due to an electric dipole. The unit of potential is volt. You know it beforehand only. Now let us consider the electric dipole again. This is minus charge and this is say plus charge. The distance between the two, say 2a. Let us consider any point. Any point means I will not take it at exactly the axial line or at an equatorial line. I'll take somewhere, say here. Say point P at a distance R from the center of the dipole. So this distance is now A. This distance is now A. This dipole can be taken as placed at point A. This charge say at point B. Now for finding out the potential, I must know the distance also from the charge to the point. So these will be the distances. And these distances will change according to the point P. Now the direction of the dipole is this, minus to plus. Let this make an angle theta with this axis. Now the potential at any point will be the sum of the potential because of charge minus q at point A plus the potential at point P due to the charge at B. So my total potential will be equal to potential due to charge A plus potential at point B due to charge plus Q. So what shall be VA equals to? VA will be equal to 1 by 4 pi epsilon naught minus Q upon R. And what is R? R is the distance of the charge and the point P. So the distance is A, P. Similarly, VB will be equal to 1 by 4 pi epsilon naught Q upon PB. Now the question arises, what is the value of AP and PB? First what we will try is draw a perpendicular from point P on OP. You can take the center as say O. And for this charge, extend this line and drop a perpendicular from point A on this line. This will be the perpendicular. Let this point be C and let this point be D. Now the distance of this AP, I have to calculate the value, and this PB also I have to calculate the value. For this what I will do is, first I will calculate the value of OC and OD. OC and OD. Now you can use your trigonometric ratio for this. The value of OC will come out to be A cos theta. That is AO cos theta. See, this angle is theta. This angle will also be theta. Now this triangle is a right angled triangle in which I want to calculate the value of OC, and what is known to me? The angle theta inside A. So using the trigonometric ratio for cos theta, OC will come out to be A cos theta, and OD also will come out to be A cos theta. Using this expression, what will be PB now? PB will be R minus OD. R minus A cos theta, and PA will be R plus A cos theta. Now we'll substitute it here. What we'll get? VA is equals to 1 by 4 pi epsilon naught minus Q. AP is R plus A cos theta plus VB 1 by 4 pi epsilon naught Q upon R minus A cos theta. Now we'll find out the value of V. V will be equal to now 1 by 4 pi epsilon naught. Since this is of negative sign VA, so I can take it afterwards. I'll take Q first, and Q can also be taken as common. 1 upon R minus A cos theta minus 1 upon R plus A cos theta. This will give you 1 by 4 pi epsilon naught. You can take the LCM. R square minus A square cos square theta, and this will be R plus A cos theta minus R plus A cos theta, minus R, so minus R plus A cos theta. This is going to give me V equals to, Q is already common, Q upon 4 pi epsilon naught, R and R will cancel out, 2A cos theta upon R square minus A square cos square theta. In place of Q into 2A, I can again place P, electric dipole moment. So P into cos theta 1 upon 4 pi epsilon naught upon R square minus A square cos square theta. This will be the expression for potential at any point due to an electric dipole. Now for a point dipole or an ideal dipole. For a point or an ideal dipole, I can neglect A, that will be very small. So V is equals to 1 upon 4 pi epsilon naught P cos theta upon R square. For an ideal dipole, R, you can say R is very much greater than A, or A is very, very small. So this will be an expression for electric dipole at any point. Now from this expression you can find out for axial point as well as for equatorial point. So you can see for an axial, so for axial point theta will be 0, and if we take the equatorial point, theta will be now 90 degree. You can see if it is an axial point like this, then theta will be 0. If the point R is here, point P is here, angle theta will be 0, and if point P becomes at equatorial point, theta will become 90 degree. So what will be V axial? V axial will now, theta will be 0, so cos 0 will give me 1. So V is equals to 1 by 4 pi epsilon naught P upon R square. And what about here? At theta is equals to 90 degree. At theta is equals to 90 degree, this will give me 0. So V at equatorial point will be 0. This question that find out potential at an equatorial point of an electric dipole may come in 1 mark also and may come in 2 marks. Suppose this question comes in 2 marks, then you need not do the whole derivation as such. Now that you can do in a mathematical form in this manner. I'll just show it here. As we had done for electric field, in a similar manner we'll do it for potential. How? See, this is minus q, this is plus q. The distance is 2a, equatorial point at the center. Exactly here is the point P, straight away. This distance is under root r square plus a square. This distance is also r square plus a square. So potential at point P will be again because of potential due to charge at point A and because of point B. So it will be simply 1 upon 4 pi epsilon naught minus q under root r square plus a square whole square. So this will vanish. R square plus a square plus 1 upon 4 pi epsilon naught plus q r square plus a square. This is going to give you now 0. See what we have done. What is the difference between the two? This you always have to remember that in potential when we are calculating, you have to keep the sign in the formula itself. It does not have to do anything with the direction. Whereas in electric field and force, negative or positive sign will give you the direction. So in this manner, you can find out the potential at any point. And superposition also, principle also holds good here. From here also you can understand of the derivation that potential at any point P will be, if there are more than 2 charges also, potential because of charge at A plus potential at charge because of point B plus C and D and so on. So in this way you can find out the value of potential. Now the second thing about the potential is the equipotential surfaces. Now what are the equipotential surfaces? Now equipotential, as the name suggests, equipotential surfaces, that means potential is same. That means a surface where the value of or the magnitude of potential is same. Suppose I take a point charge. This is to understand. Say charge Q. Now my formula for finding out the potential is 1 by 4 pi epsilon naught Q upon R. Now this is constant. For whatever charge we are finding, that is also constant. So if the distance remains same of the point, then that will be having the same value of potential. So suppose I take a distance r from one side. So everywhere at a distance r, the potential will be same. That means a sphere around the charge will give me an equipotential surface. So like we have made a Gaussian surface where magnitude of electric field was same, you'll also get it in similar manner. Here, now since it is a scalar quantity, so value will be same. Whereas in that case, since directions were different at different places, so we say that electric field is not same at all the points. So equipotential surface, say a point charge will be spherical in nature, like this. You got to make a sphere of given constant radius using a compass. In examination, sometimes it is asked, draw an equipotential surface or draw two equipotential surface for a point charge. So for a point charge, equipotential surfaces will be like this. You just write down here, label like this, 1, 2 and 3. These are equipotential surfaces. If 2 are asked, to draw 2. If 3 are being asked, draw 3. For a uniform field or for a uniform surfaces, it will be again simple plain lines. So equipotential surface for a point charge will be like this. You draw it like this. And electric field, as you all know, will always be perpendicular to the given equipotential surface. You have already drawn electric field lines. Like for a uniform field, electric field, uniform field, equipotential surface will be plane surfaces like this. And you can just write down number 1, number 2. If 3 are being asked, draw 3. So 1 and 2 are, you can write down on the sides, there's the surfaces numbered 1 and 2 are equipotential surfaces. Now equipotential surfaces will be shown farther away from each other if the values are continuously decreasing or increasing accordingly. The main property of this equipotential surface is that on an equipotential surface, the work done will be 0. See, we already had formula VB minus VA is equals to work done in moving a charge from A to B if the charge is, say, Q naught. See, if the potential is same at 2 points, suppose I take point A here and point B here, they are at the same potential. I want to move a charge from point, say, A to B or B to A. Since these two values are same, this is going to give me 0 and therefore work done will be 0. This is a very common question being asked. It can be asked in a manner, say there is a charge of, say, 100 microcoulomb. We want to make another charge of, say, 5 microcoulomb move around it in a radius of 5 centimeter. So it has to move like this. What is the work done? So work done again will be a 0. Reason being that it will be an equipotential surface. In a uniform electric field also, the work done will be 0, and that will also make a equipotential surface. No two equipotential surfaces can intersect each other. So these are the various properties of equipotential surface. What is an equipotential surface? I have told you. What is the work done? Now we can do certain questions which are based on potential. You can do from your NCERT book the solved example which are based on potential. We'll be doing potential energy tomorrow. That is the potential energy associated with a point charge and with the combination of charges. So this much you'll do, and you'll do solved example from your NCERT book. That is example 2.1 on page 55, and exercise also you can do 2.1 and 2.2. This much work you can do today. Tomorrow we'll talk about potential energy. Thank you.